Electric motors can be categorized into main category single-phase motors and three-phase motors. There are, of course, low-voltage DC motors, but that's a chapter for another day. Within the single-phase motors we have split-phase motors, resistance start induction run motors, capacitor start induction run motors, dual-voltage split-phase motors, capacitor start capacitor run motors, shaded pole induction motors, multi-speed motors, repulsion-type motors, repulsion start induction run motors, repulsion induction motors, single-phase synchronous motors, stepping motors, universal motors. In the three-phase category we have the squirrel cage induction motor, wound rotor induction motors, synchronous motors, Selson motor. Although most of the large motors used today in the industry are three-phase, at times single-phase motors must be used. Single-phase motors are used almost exclusively to operate home appliances, such as air conditioners, refrigerators, well pumps, and fans. They are generally designed to operate on 120 volts or 240 volts. They range in size from fraction of a horsepower to several and hundreds of horsepower, depending on the application. There are only many different types of single-phase motors, but they have different operating principles. Split-phase motors. The split-phase motors fall into three general classifications: the resistance start induction motor, the capacitor start induction run motor, and the capacitor start capacitor run motor. Although all these motors have different operating characteristics, they are similar in construction and use the same operating principle. Split-phase motors receive their name from the manner in which they operate. Like three-phase motors, split-phase motors operate on the principle of a magnetic field. However, a rotating field cannot be produced by a single phase. Therefore, split-phase motors split the current flow through separate windings to simulate a two-phase power system. And the magnetic field will work just fine with a two-phase system. Two-phase power. In some parts of the world, two-phase power is produced. A two-phase system is produced by having an alternator with two sets of coils wound 90 degrees apart. Therefore, the voltages of a two-phase system are 90 degrees out of phase with each other. These two out-of-phase voltages can be used to produce a rotating magnetic field in a manner similar to that of a three-phase system. Stator winding. The stator of a split-phase motor contains the separate windings, the start winding and the run winding. The start winding is made of small wire and is placed near the top of the starter core. The run winding is made of larger size wire and is placed near at the bottom of the stator core. When power is applied to the starter, current will flow through both windings. Since the start winding is more resistive, the current flow through it will be more in phase with the applied voltage than will the current flow through the run winding. The current flow through the run winding will lag the applied voltage due to inductive reactance. These two out-of-phase currents are used to create a rotating magnetic field in the stator. The speed of this rotating magnetic field is called synchronous speed and is determined by the same two factors that determine the synchronous speed for a three-phase motor. First, the number of stator poles per phase, and frequency of the applied voltage. Resistance start induction run motors. The resistance start induction run motor receives its name from the fact that the out-of-phase condition between start run winding current is caused by the start winding being more resistive than the run winding. The amount of starting torque produced by the split-phase motor is determined by three factors. First, the strength of the magnetic field of the stator. Second, the strength of the magnetic field of the rotor. And third, the phase angle of the difference between current in the start winding and current in the run winding. Maximum torque is produced when these two currents are out of phase with each other. Direction of rotation. The direction of rotation for the motor is determined by the direction of rotation of the rotating magnetic field created by the run and start winding when the motor is first started. The direction of the motor rotation can be changed by reversing the connection of either the start winding or the run winding, but not both. If the start winding is disconnected, the motor can be operated in either direction by manually turning the rotor shaft in the desired direction of rotation. Capacitor start induction run motors. Capacitor start induction run motor is very similar in construction and operation to the resistance start induction run motor. The capacitor start induction run motor, however, has an AC electrolytic capacitor connected in series with the centrifugal switch and start winding. Although the running characteristics of the capacitor start induction run motor and the resistance start induction run motor are identical, the starting characteristics are not. The capacitor start induction run motor produces a starting torque that is substantially higher than that of the resistance start induction run motor. Although the capacitor start induction run motor has a high starting torque, the motor should not be started more than 8 times per hour. Determining the direction of rotation for split-phase motors. Direction of rotation of a single-phase motor can generally be determined when the more it is connected. The direction of rotation is determined by facing the back or rear of the motor. What I personally do to determine rotation is I use the jogging method. I run it for a split second and check rotation. Capacitor start capacitor run motor. Salta. The capacitor start capacitor run motor is a split-phase motor. It operates on a different principle than the resistance start induction run motor or the capacitor start induction run motor. The capacitor start capacitor run motor is designed in such a manner that in the start winding energized at all times. A capacitor is connected in series with the winding to provide a continuous leading current in the start winding. Since the start winding remains energized at all times, there is no need for a centrifugal switch. The capacitor type usually used in this type of motor is of oil-filled types and since it is intended for continuous use. Shaded pole induction motors. Shaded pole induction motor is popular because of its simplicity and long life. This motor contains no start windings or centrifugal switch. It contains a squirrel cage rotor and operates on the principle of a rotating wound on one side of each pole piece. Shaded motors are generally fractional horsepower motors and are used for low torque applications such as operating fans and blowers. The shading coil. Shading coil is wound around one end of the pole piece. The shading coil is actually a large loop of copper wire or a copper band. The two ends are connected to form a complete circuit. The shading coils acts in the same manner as a transformer with a shorted secondary winding. When the current of the AC wave increases from zero towards its positive peak, a magnetic field is created in the pole piece. As magnetic flux cuts through the shading coil, a voltage is induced in the coil. Since the coil is a low-resistance short circuit, a large amount of current flows in the loop. The current causes in opposition to the change of magnetism flux. As long as voltage is induced into the shading coil, there will be an opposition to the change of magnetic flux. When the AC current reaches its peak value, it is no longer changing, and no voltage is being induced into the shading coil. Since there is no current flow in the shading coil, there is no opposition to the magnetic flux. The magnetic flux of the pole piece is now uniform across the pole face. When the AC current begins to decrease from its peak value back towards zero, the magnetic field of the pole piece begins to collapse. A voltage is again induced into the shading coil. The induced voltage creates a current that opposes the change of magnetic flux. This causes the magnetic flux to be concentrated in the shaded section of the pole piece. General operating characteristic. The shaded pole motor contains a standard squirrel cage motor. The amount of torque produced is determined by the strength of the magnetic field of the stator, the strength of the magnetic field of the rotor, and the phase angle difference between rotor and stator flux. The shaded pole induction motor has low starting and running torque. The direction of rotation is determined by the direction in which the rotating magnetic field moves across the pole face. Multi-speed motors are two basic types of multi-speed single-phase motors. One is the consequence pole type and the other is a specially wound capacitor start capacitor run motor or shaded pole induction motor. The consequent pole motor is used where high running torque must be maintained at different speeds. A good example of where this type of motor is used is in two-speed compressors for central air conditioning units. Multi-speed fan motors. Multi-speed fan motors have been used for many years. These motors are generally wound for 2 to 5 steps of speed and operate fans and squirrel cage blowers. The start winding is connected in parallel with the run winding section. The other end of the start winding leads is connected to an external oil-filled capacitor. This motor obtains a change of speed by inserting inductance in series with the run winding. The actual run winding for this motor is between the terminals marked high and common. Common speeds for a 4-pole motor of this type are 1650, 1500, and 1350 rpm. Notice that this type of motors don't have a wide range between speeds as would be the case with a consequent pole motor. Most induction motors would overheat and damage the motor winding if the speed were reduced to this extent. This type of motor, however, has much higher impedance windings than most motors. The run windings of most split-phase motors have wire resistance of 1 through 4 ohms. This motor will generally have a resistance of 10 through 15 ohms in its run winding. It is the high impedance of the windings that permits the motor to be operated in this manner without damage. Since the motor is designed to slow down when load is added, it is not used to operate high torque loads. This type of motor is generally used to operate only low torque loads such as fans and blowers. Repulsion type motors. There are 3 basic repulsion types of motors. First, the repulsion motor. Second, the repulsion start induction run motor. And third, the repulsion induction motor. Construction of repulsion motors. A repulsion motor operates on the principle that like magnetic poles repel each other, not under the principle of a rotating magnetic field. The stator of a repulsion motor contains only a run winding very similar to that used in the split-phase motor. Start windings are not necessary. The rotor is actually called an armature because it contains a slotted metal core with windings placed in the slots. The windings are connected to a commutator. A set of brushes makes contact with the surface of the commutator bars. The entire assembly looks very much like a DC armature and brush assembly. One difference, however, is that the brushes of the repulsion motor are shorted together. Their function is to provide a current path through certain parts of the armature, not to provide power to the armature from the external source. Repulsion start induction run motor. The repulsion start induction run motor starts as a repulsion motor, but runs like a squirrel cage motor. There are two types of repulsion start induction run motors. First, the brush riding type, and second, the brush lifting type. The brush riding type uses an axial commutator. The brushes ride against the commutator segments at all times when the motor is in operation, after the motor has accelerated to approximately 75% of its full load speed. Centrifugal force causes copper segments of a short-circuiting ring to overcome the force of a spring. The segments sling out and make contact with the segments of the commutator, and the motor operates in the same manner as a squirrel cage motor. Repulsion induction motor. The repulsion induction motor is basically the same as the repulsion motor except that a set of squirrel cage winding are added to the armature. This type of motor contains no centrifugal mechanism or short-circuiting device. The brushes ride against the commutator at all times. The repulsion induction motor has a very high starting torque because it starts as a repulsion motor. The squirrel cage winding, however, gives it much better speed characteristics than a standard repulsion motor. This motor has a very good speed regulation between no load and full load. Its running characteristics are similar to a decompound motor. Single-phase synchronous motors are small and develop on the fractional horsepower. They operate on the principle of a rotating magnetic field developed by a shaded polestator, although they will operate at synchronous speed. They do not require DC excitation. They are used in applications where constant speed is required, such as clock motor, timers, and recording instruments. They also are used as the driving force for small fans because they are small and inexpensive to manufacture. There are two basic types of synchronous motor, the Warren, or General Electric, and the Holtz motor. These motors are also referred to as hysteresis motors. Warren motor is constructed with a laminated stator core and a single coil. The coil is generally wound for 120 volts AC operation. The core contains the poles, which are divided into two sections each. One half of each pole piece contains a shading coil to produce a rotating magnetic field. Since the stator is divided into two poles, the synchronous field speed will be 3,600 RPM when connected to 60 Hz. The difference between the Warren and Holtz motors is the type of rotor used. The rotor of the Warren motor is constructed by stacking hardened steel laminations onto the rotor shaft. These discs have high hysteresis loss. The laminations form the crossbars for the motor. When power is connected to the motor, the rotating magnetic field induces a voltage into the rotor. The rotating fields induces a voltage into the rotor, and a strong starting torque is developed, causing the rotor to accelerate to near synchronous speed. Once the motor has accelerated to near synchronous speed, the flux of the rotating magnetic field will follow the path of minimum reluctance, or magnetic resistance, through the two crossbars. This causes the rotor to lock in step with the rotating magnetic fields, and the motor operates at 3,600 RPM. These motors are often used with small gear trains to reduce the speed to the desired level. Holtz motor uses a different type of rotor. This rotor is cut in such a manner that 6 slots are formed. These slots form 6 salient or projecting poles for the rotor. A squirrel cage winding is constructed by inserting a metal bar at the bottom of each slot. When power is connected to the motor, the squirrel cage winding provides the torque necessary to start the rotor turning. When the rotor approaches synchronous speed, the salient poles will lock in step with the filled poles each half cycle. This produces a rotor speed of 1200 RPM, 1/3 of the synchronous speed for the motor. Stepping motors are devices that convert the electrical impulses into mechanical movement. Stepping motors differ from other types of DC ORC motors in that their output shaft moves through a specific angular rotation each time the motor receives a pulse. The stepping motor allows a load to be controlled as to speed, distance, or position. These motors are very accurate in their control performance. There is generally less than 5% error per angle of rotation, and this error is not cumulative regardless of the number of rotations. Stepping motors are operated on DC power, but can be used as a two-phase synchronous motor when connected to AC power. AC operation stepping motors can be operated on AC voltage. In theme mode of operation, they become the phase AC, synchronous, constant speed motors and are classified as a permanent magnet induction motor. This motor has no brushes, slip rings, commutator, gears, or belts. Bearings maintain a constant air gap between the permanent magnet rotor, the stator windings, a typical synchronous speed of 72 RPM when connected to a 60 Hz, two-phase AC power line. Universal motor is often referred to as an AC series motor. This motor is very similar to a DC series motor in its construction in that it contains a wound armature and brushes. The universal motor, however, has the addition of a compensating winding. If a DC series motor were connected to alternating current, the motor would operate poorly for several reasons. The armature windings would have a large amount of inductive reactance when connected to alternating current. Another reason for poor operation is that the field poles of most DC machines contain solid metal pole pieces. If the field were connected to AC, a large amount of power would be lost to eddy current induction in the pole pieces. Universal motors contain a laminated core to help prevent this problem. The compensating winding is wound around the stator and functions to counteract the inductive reactance in the armature winding. The universal motor is so named because it can be operated on AC or DC voltage. When the motor is operated on direct current, the compensating winding is connected in series with the series field winding, connecting the compensating winding for a current. When the universal motor is operated with AC power, the compensating winding can be connected in two ways. If it is connected in series with the armature, it is known as conductive compensation. The compensating winding can also be connected by shorting its leads together. When connected in this manner, the windings acts like a shorted secondary winding of a transformer. Induced current permits the winding to operate when connected in this manner. This connection is known as inductive compensation. Inductive compensation cannot be used when the motor is connected to direct current. Neutral planescence. The universal motor contains a wound armature, commutator, and brushes. The brushes should be set at the neutral plane position. This can be done in the universal motor in a manner similar to that of setting the neutral plane of a DC machine. Speed regulation of the universal motor is very poor. Since THS motor is a series motor, it has the same or speed regulation as a DC series motor. If the universal motor is connected to a light load or no load, the speed is almost unlimited. It is not unusual for this motor to be operated at several thousand revolutions per minute. Universal motors are used in a number of portable appliances where high horsepower and light weight are needed, such as drill motors, skill saws, and vacuum cleaners. The universal motor is able to produce a high horsepower for its size and weight because of its high operating speed. The direction of the universal motor can be changed in the same manner as changing the direction of rotation of a DC series motor by changing the armature leads with respect to the field leads. Thank you. Tomorrow we tackle three-phase motors. Please like, share, and subscribe.